Okay, so what is deep learning? So we learned neural networks last time, right? Neural networks is just this idea. I take something very basic like this unit here, which is a perceptron. Okay, perceptron we already know. It has a bias weight, right? This is our bias. Okay, and we're just going to make this into x0, which is always observed as 1. And then I have, whatever number of features up until d, right? So this is the same thing that you saw earlier. We have all of these weights incoming. I'm going to aggregate them through a summation of the weights times the feature values, and then output as signal, right? That's linear. Okay. Now, when I'm doing deep learning, the only difference is I get to stack more layers. Okay. Instead of having, let's say, 2 layers, I might have, you know, uh, 5 layers, 10 layers, or even 1,000 layers. Okay. So it just means I have built a much larger structure. That larger structure has more units. More units obviously means I need more weights, right? So each of these blue edges with an arrow is a weight, right? Because I have a weight that's tied from a particular input, okay? From a particular input, let's say this input, to a particular output, right? So I have this particular weight here. That weight has to, that edge has to have a weight, right? We learned how to specify weights in the topological um, what was it, a tensor last week, right? So it's a three-dimensional object, okay? So that's all there is to it, right? So in this week, in week 10, I should say 10, not 11, we are actually doing ensembling, right? The idea that we are going to take all of this information and then from one layer and feed it into another. So stacking is one model of ensembling, okay? So actually, deep learning can be deep just because we're stacking multiple layers on top. You usually mean a connectionist algorithm, okay? If you remember all the way back to paradigms of machine learning, we talked about Pedro's idea of having different families or different tribes of machine learning, okay? And one that resonates very well with deep learning is the really, really simple algorithms that we have learned in linear networks, right? Just very simple aggregates of weights times their features, okay? So that's what deep learning is, okay? And as I said, there are different ways of characterizing to deep, okay? Why is deep learning so important? Well, because deep learning has actually a lot of wins in being able to represent any target function, okay? Like we saw before in the previous universal approximation theorem that was shown to you graphically, even something as simple as a 2-layer neural network, we can array, if we are given unlimited amount of units, we can represent any function very easily, okay? So the important thing about deep learning is that we, instead of doing that, we can actually pull together lots of layers and use many, many fewer parameters, okay, than the 2-layer network to represent the same thing. Because basically, when I put a node at an upper layer, it is actually operating over all of the inputs at the lower layer, right? So it can illustrate much more complex behavior, okay? So this is why we say we don't need that many more elements, even though I could have had a lot at a single layer. By having fewer at each layer, but having more depth, I can get the same amount of expressiveness, okay? And that a generalization also comes at a case when we can represent things at an abstract level. Like I was saying earlier in transfer learning, maybe we would want a circle detector, but that circle detector would be used in several different places. Okay, so having it at a sufficiently high layer would allow it to be used instead of constructing a circle detector at each part of the image, for example. So that generalization capability is being illustrated by the fact that we can put detectors that are building over more primitive features at a lower level. Okay, so actually, if you think about it, most of what we think in as the key structural ideas of neural networks, it's the same in deep learning, okay? It's just at a much larger scale, all right? But the algorithms, if you know historically, okay, the backpropagation algorithm was created in the late 80s. The idea of stochastic gradient descent for learning has been around since the 60s or 50s, in the last century at least. Okay, so these technologies, or the math for it, has been around for a very, very long time. And people had been thinking about building neural networks for a long time, but they weren't popular until recently. Okay, and there's really three key problems. Okay, the computational complexity. It's very typical when you talk about neural networks these days, deep neural networks, you're talking about millions of parameters or billions of neurons. Okay, so you can see when you use that type of magnitude to express the model, it's going to require a lot of computation, even though that computation is very simple, just multiplying and adding for the most part. Okay, there were other problems. Okay, we talked last week about the vanishing gradient problem, right? When you stack a neural network with multiple layers, the gradient at these two areas, okay, when we're taking very positive signals, ones that are close to infinity or negative infinity, they basically have no gradient left, because if you look at the slope of the line in these two boxes, it's close to zero. Okay, so when there's no gradient, then there's very little I can do to update my weights. You can say, well, I'm in a very flat region. I don't know where to tune, because basically the weights, even though they might get slightly better, it's like walking in a flat area. You have to watch the rain puddle in order to figure out which way is down. Okay, so to minimize a loss in a vanishing gradient area is very difficult. Okay. And for quite a long time, people weren't looking at this because, computational learning theory had developed a very good math, okay? Ones that we haven't taught you about SVM, okay? That shows us the sort of like uh, more advanced mathematics to show how many parameters you really need to be able to express a good function, okay? So because support vector machines worked very well in the 90s, and so there was no point in looking at neural networks. Okay, but that changed, right? And we all know it. I mean, many of you have been absorbing the big data and neural network schemes for the last, I don't know, 5 or 6 years. And it's really due to these three things, okay? 1, 2, and 3. The first is big data. All right. Now, of course, when you were growing up already, there was big data around, but certainly every year we see there's more and more content being available, right? Inevitably, as we write our social media, take pictures with our phones, okay, we're gathering megabytes, gigabytes, terabytes of data, and they're all going up into the cloud, okay? So all of these data are being mined by algorithms, and then that means if we want to make sense of them, there must be a model architecture that can really absorb that amount of data and make sense with it. Okay, the previous cohort or generation of algorithms from support vector machines and earlier algorithms basically could do well with medium-sized data sets, but they couldn't do very well in generalizing against the very, very large data sets that they saw coming. Okay, the second part was hardware support. If you had very large models, that means you had to compute them, right? So computing them was a problem on a CPU, because basically you would have to chain all of these calculations together and do them one by one. So imagine if you have a very large set of multiplications to do, you would have to do them all serially on a CPU. Okay, thanks to the fact that PlayStations and Xboxes came about, okay, these vendors needed to create architectures that could process lots of computation in parallel, okay? And it turned out that computation that's done on what we call a graphical processing unit, or GPU, was absolutely a good fit for what we needed to do when we wanted to compute large models. We want to do the same things that we've already done for linear models, which is, take a dot product, okay? Add things together, okay? Forward it to the next level, okay? And all of these very simple arithmetic functions can be done in parallel for very cheap time cycles on a GPU. Okay, so the whole idea is like, okay, we created GPUs for gaming, but they suddenly turned out to be a perfect fit. I mean, really perfect for computing large scale tensor and matrix multiplications. okay? And then, those two were very important, but we still needed some particular algorithms to make it feasible to actually train large scale, okay? And so we'll learn a couple of these. One is pre-training or autoencoding, so being able to initialize a neural network well so it can train well. Having good regularization, again, with billions of parameters, how do you know which ones are actually not overfitting, okay? So we want to try to regularize this so that we don't depend too much on any individual neuron. And like we saw on the L1 and L2 regularizers, making sure they don't have big weights, right? Because big weights cause the matching function to fluctuate a lot. And then we get a lot of variance error, okay? And the third one is ReLU, right? We wanted to address the problem that we illustrated in the earlier lecture on vanishing, and correlated problem is exploding gradients, okay? Both of these cause learning in the stacked type of implementation where we layer upon layer of neurons. It didn't work at the beginning, okay? So we had to address that, and changing from a hyperbolic tangent and a sigmoid function to something even simpler, something like a ReLU, caused us to solve this problem. Okay, so how does it work? Unfortunately or fortunately, you are learning things that even your lecturer has a hard time keeping up with, because things are changing very fast, okay? Things that you are learning are updated basically every couple of months, okay? So this also means that you have to think about what can be generalized from this, because there will be certain things that we teach you that may not survive for more than a couple of years' time, okay? So you hear about, your skills being outdated very fast. That happens in machine learning too, because things are going very quickly, okay? So what I'll say is, try not to overfit too much on your model. The core tenets of what we're trying to teach you in this class about overfitting, bias, variance, they will always be around. They're mathematically correct and functioning. Okay, when we think about neural networks, we still don't have all the right answers about why these things work so well. And so our understanding is sort of lagging our application of it. And this is very, very dangerous, right? As you'll see in our ethics lecture at the end of the course, when you use things that work and you don't understand why, that is usually a problem, okay? So we'll get to that later, okay? The point is right now is that deep learning is really an evolving area, and you should be open and mindful of the new advances that are coming about, especially if you're interested in this area and you want to follow it through into your postgraduate or higher level studies in year 4, for example. Okay, so the very key idea of deep learning is very simple, okay? We want to get more expressiveness with fewer parameters, okay? Now you've heard me already say, okay, these deep learning models have millions of parameters, okay? We are going to deal with that, okay? But the whole point is, like, if your data is very, very large, simple models cannot fit the signal enough. There's too much bias errors. Those simple models just don't have enough expressiveness to fit the data very well, okay? So what we want is a scalable way of using more data points, having more parameters, but doing it in such a way that we don't run into this bias variance trade-off, okay? So we're going to do all of this, right? We're going to add more capability of our model, okay? We're going to add more networks, more layers, okay? So we'll have less bias error because our model will be able to fit better. But of course, when we add more and more of these connections, all of those weights, right? And our theta becomes a tensor, and there are millions of parameters, okay? That means we have to be able to set every one of these millions of parameters correctly in order for our neural network to function well, okay? Well, if you have that, then maybe, you have so many parameters that we don't have enough data to set any of them very well. If that's the case, then our generalization is going to suffer, all right? We're not going to get very good output out of this. We want to choose a model representation that's likely to fit the signal. So we want to find representations that embody good ones, okay? So you can recall the bias variance lecture where we said we want to have an expressive model, but we want it to be, we want to set our parameters in a way that encourages the setting of those parameters to be close to what a good representation would be, Okay, so again, no wild waving functions where the coefficients are set at a very high value. Okay, so I'm just going to check to see whether we have any more things. Okay, we do have a couple more questions, so I will get back to that. Okay, so in deep neural networks, basically what we're trying to do is take a look at that large network that we had before, this one here, okay? Okay, this set of neurons here, you can see all of these are fully connected, okay? Meaning that every node in one layer is connected to every node in its intervening layer, okay? Could we be a little bit smarter about that? Do we really need all of these connections? Maybe we can have fewer and use them in some topologically motivated way to abet a better representation of learning. Okay, that's the idea behind deep learning. Okay, so there are a couple different types that you'll see. Okay, the ones that we are learning in this lecture is confined to what we call the CNN and RNN. Okay, there are actually two RNNs. Okay, there's a RNN that's a recurrent, meaning having sequence. You know, I have one time step, then another time step, like days of the week. Okay, or audio signal that I might be speaking in a waveform and sampling at several milliseconds at a time. Or for example, natural language processing where I have words coming in at a time, okay? And that would be a recurrent neural network, okay? There's another one called a recursive neural network, which is to look at structured data. So you can think about layers of things on top of each other. So that could be something like a decision tree or other things where there's some structure, internal structure to the data, okay, which could be recursively defined. Okay, so recursive neural network deals with that. We will talk more about the CNN. The CNN is a convolutional neural network. You can just think of this as looking for some spatially motivated regularity in an image, right? So for example, here you have 4 cans of soup, you know, so we would say, you know, if I can detect a can of soup here, then, you know, that same detector might fire over here, and then over here, and then over here, okay? So actually, I only need one detector to find this soup can. It's just gonna be applied in 4 different areas with 4 different types of colors, etc. Okay, and the final one that some of you may have heard of is something called a generative adversarial network. It's basically the idea that you have a game, okay? A game where one neural network is playing a game against another. So one neural network might be trying to classify images and another neural network might be trying to create images that would fool the first network into thinking that this is a real image or not, okay? So that's why we call it an adversarial network. And the second network that's generating information is why it's called a generative adversarial network, okay? So a generative adversarial network we're not going to touch upon, but just so that you know, it's basically another type of optimization structure to help you do better by planting an adversary who's trained with you to try to fool you and to help you get a better idea of a loss function, okay? So you could think about it as, let's say, a friend or a tutor who's testing your understanding of a concept. You know, is this a dog? You know, is that a cat? And then giving you borderline cases. What do you think about this image? Is it a dog or a cat? Because it looks a little cat-like, but it's actually a dog, okay? So things of this sort are what a generative adversarial network is good for. Okay, so there are lots of different terminology that you'll see in deep learning. Some of them are what are pretty easy to understand. So when we say a dense layer or a fully connected layer, it's that case where we saw in the first slide or so, okay, here, where basically you have layers that are next to each other that are fully connected. No edges are missing, okay? That's what we mean by a fully connected layer, okay? So let me go back. 13. Yeah, okay. So there are other layers as well, okay? One that's called a pooling layer or a subsampling layer. We'll talk about this in a while. A convolution layer, which is looking for things locally. A nonlinear activation, okay, which could be a layer on its own if you think about it as a composition function. an attention layer that would, which we're not going to talk about. These two we're not going to talk about, but these are different layers that you'll see in certain architectures, okay, to help the network um, look for certain specific types of features, okay? And activations, okay, there are lots of different activation functions that we can use. We already talked about the sigmoid and hyperbolic tangent and why they have problems. And then there's a couple other functions that you'll see, which is the ReLU, the leaky ReLU, and the max out, which basically try to remove the problems with vanishing gradients that we have with sigmoid and hyperbolic tangent. Again, the same things are in here, where we have a S function where at the tails, the gradients are very flat. Okay, so this is no good. So we want to make sure that we always have a gradient when something is happening. So we can use a ReLU, right? The ReLU function looks like this. So there's always a gradient up here. And then we've just made a nonlinearity by setting no gradient for negative numbers, okay? Negative incoming, okay? So let's first talk about what a recurrent neural network is, okay? A recurrent neural network looks like the one on the right, okay? On the left, we have our standard non-recurrent neural network where we have an input, right? It goes through a bunch of layers. So you might say, okay, layer here, layer here, layer here, okay? And then I have some output, okay? So here's whatever I decided to calculate. Okay, so that's a standard neural network. So this green bubble here basically is trying to say the entire body of the network minus the last layer, which is actually doing the hypothesis calculation. Okay, now in a recurrent neural network, what we're saying is we're getting the same inputs outputted at each time and sent back to itself, okay, upon different time steps, okay? So it's most easily visualized in this, okay? So let's say we have this neural network, okay? So you have two nodes, okay, two inputs at one time, okay? We have our two inputs down at the bottom, okay, over here, okay? And then after that, it's going through a number of hidden layers, right, in the green. And then after that, we have an output. Okay, now let's say, sorry, we get another two timestamps, okay? So in these two timestamps, we get additional inputs, okay? So for example, I get two more inputs at time 0.2 and two more inputs at time 0.3, okay? Now, instead of saying each time point, I have a different neural network that I have to train for. What I'm going to do is take the same neural network, the one that I created at the beginning, okay? And I'm going to train that same neural network at all of the timestamps, okay? Okay, the only difference is I need to feed in past history, okay? If you remember from reinforcement learning, right? We said, I need to know in a Markov model or a Markov decision process, what happened at the last round, okay? That's exactly what we're doing in RNNs, okay? We say, in order to know or how to decide what to do at this time step, okay, I need to know what happened at this time step, okay? How do I do that? I take all of these purple edges, okay? So for example, at this node here, okay, this middle A, okay, this one over here, all right, I need to know what happened at the nodes that came from below. Okay, so let me just draw that, this one, and this one. But I also need to know what happened to this node, okay? Myself, back one time step, okay? What did I do, okay? And so this particular output follows this path here, okay? So actually, this node is getting information from its past self as well as the inputs that it normally does, okay? And we are training this entire network, just moving it down by looking at multiple time steps. So even though this copy of this diagram looks complicated. It's not actually that complicated because all I have are the normal weights that we would see in this one, okay? But additionally, having another set of weights, okay, coming from the previous timestamp, okay? So that's all it is. So instead of having, we just have one more set of weights coming from the previous timestamp. And all of these weights are being trained simultaneously. Okay, so you can see what that looks like. There are lots of different sequence problems that we can have. Typically, we can think of things like this case here, okay, one to many. So I have a particular input and I have to create a sentence with it, okay? So I have to take that sentence and write out a sentence. So I have one input and I have to output multiple words, okay? Or I can have a input that consists of multiple time steps, okay? For example, price history of a stock, okay? And decide something at the end. Should I buy or should I sell, okay? I could also do something like many to many. So at every time point, I need to make a decision. So this could be the same stock market example, right? Every day I get a new time point and every day I have to decide whether to buy or sell, okay? But of course, that's going to be based on historical information that I'm passing down, okay? And then this one is my personal favorite. This is like natural language translation, okay? I get a sentence here in English and I want to translate it into a sentence in Chinese, for example, okay? So I basically build up a representation over several time steps until I get to a representation of the entire sentence, okay? What does this sentence mean, okay? And this sentence meaning is then gradually described in another language in the outputs, okay? All right, so that goes over this simple idea so far about what we mean by a recurrent network, right? A recurrent network just means that I have information that's going over different time stages, okay? So I'm using the same neural network with few parameters, but I'm using it at every time step, okay? So I can reason with it and not build such a huge network, right? If I have to build a real huge network, I would have one part of the network responsible for each time step. But what I'm doing is I'm conserving it. I'm saying for every sentence, for every words, I'm just using the same neural network to do whatever function I need. Okay, so convolutional neural networks, you should remember, is based about spatial features, okay? So let's take a look at an image. This is an image of a 6, okay? So what I'm going to do is take this input and transform it into a single vector, okay? And that's really easy. I can take this raster image, write it in grayscale, write it as a bunch of lines, okay? So it's basically one long array, okay, a linked list or a one-dimensional array of inputs, okay? And I might draw it as a bunch of column vectors, although, you know, you can just think of them as X values, okay? So there's some confusion by other students about whether this represented that we had to transpose everything. No, okay, it's just easier to show, okay? And then I'm gonna send all of these as inputs, right? These are my gray nodes here, okay? And then what I want to do with these gray nodes is pass them through a neural network, right? So for example, when I look at this neural network, let's say I have very strong activation weights here, okay, just for this part here, okay? And all of the other weights down here, they're all not on, they have a strong negative weight, okay? And then what I want to ask you is, what type of thing is this thing doing then? Okay, if it only activates or outputs some value to its downstream nodes, okay, when these things are positive and these things are negative, okay, okay, then what is it doing? Okay, if you've got an answer for me, please go ahead and type it in your chat, or maybe you can tell me what you think, okay? Anyone following? So if you have an idea, can you please let me know? Yeah, so it's only looking at the first row in the picture. That's right. What could it be doing? Yeah, so Li Shuo is right. So if the weights on the edges at the top are strongly on, right, and these ones are all off, the ones down here, okay, then it's looking for a horizontal line at the top. Okay, does that make sense? Okay, I'm missing an L, so let me just add it in there. Okay, basically, I'm only giving output if most of the pixels here, or most of the inputs that I'm receiving, are turned on. Okay, and I really don't care what's happening in the rest. Okay, I'm just going to discard that information. Good, thank you, Li Shuo. So let's go on to the next one. What about this one? Okay, this one looks a little bit strange, right? Basically, it's got some cases where just at the beginning of each line, these are on, these are positive, okay? But then the rest of these are all negative, okay? What could it be doing? Well, assuming the rest of the things here are all negative, so the rest of the rows are all negative, you can see what it might be doing. You have 3 lines that are on for positive. Okay, so basically it's looking at the top part of the image. Okay, only looking at this part of the image. Okay, top or left corner. Okay, so that's what it's doing in this case. All right. So this is the whole idea of a convolution, okay? So what we're going to define are a set of weights, okay? These weights we're going to call a kernel, okay? And this kernel is defined as a set of scalar values, which we're going to multiply against an input field, okay? You can see the input field here is moving around, right? So basically what we have here is, let's say the yellow part is being multiplied against our kernel, right? And then those values are being added together. You know, it's basically our features times our input, right? And then sum together and then written here, okay? So you can take a look at this part here. You multiply it against this matrix here, and you can see that this one, this one, this one, and this one are all times 1. Then we add them together to get this 4. Okay? All right. So what a kernel function is basically it's a set of weights, okay? It's a set of weights that are connected to a neuron, okay? But those set of weights are being slid across the image, okay? And this is creating a convolved feature, or what we call an activation map, okay? So I'm going to show you this website. I highly recommend that you look at it. Okay, so I'm just going to bring it over here. Okay, and I hope my computer is not going to die on me. Okay. So you see this all the time when you actually use software. Okay, so for example, if you use Photoshop or something like that, you can blur out an image, right? Blurring an image makes it look like the one on the right. We just do this by convolving a feature map. This is our feature map, the one that we just saw in the left-hand side of the slide, right? Sorry, not this one, this one. Okay, that's our feature map. This is our free by free kernel or feature map. Okay, we're multiplying it for every pixel that we're looking at, right? So let's say I'm looking at this person's left eye. Okay, I'm centered exactly over that. I'm multiplying all these values in the box, the red box, times the actual pixel values, which you can see as these numbers down in the, let's see, let's make it green box here, okay? And then I sum them all together and get the result 95, which I'm putting right here, okay? that's how we blur, right? We just basically try to smooth out all the values, right? On the other hand, if I decide I want to do something like sharpen, let's see, okay, then basically you can see what it's doing, right? It's basically saying, look at the color or the grayscale right at the middle and penalize if there are other things nearby that are also on. So I'm looking for something that's an edge. I'm looking for something that's pixelated, right? So I'm going to make the things like this eye here prominent this way, because the eye has a dark pixel in the middle, which is going to be times by 5, and the other white regions next door are going to be subtracting away weight. Okay, so you can play with this to get some idea of what's going on. You can try different things, like you can try what happens if I have a left detector. Okay, then I can see very straight edges here, right? I can see what I would see if I have a top detector. You can see it finds horizontal lines very easily, okay, by virtue of having this kernel, okay? Okay, so this is the idea of a convolutional filter, right? So basically, when I do that, and I have these different features that are going to be set after optimization by stochastic gradient set, it'll just find the right weights for these. We can find things like vertical lines, okay, or horizontal lines, or small circles, okay? Now, these things are going to be in specific places right now, because I have a feature at a specific point, okay? Now, if I do this actual work that I want to do, which is sliding it, as I said, sliding this detector over multiple regions, okay? I can get away with not having to worry about this specific problem about having a detector only in a specific place, okay? That detector can fire because that detector slid over the entire image, okay? So we can also get this by using this at a higher level neuron. So imagine if I took that detector that we saw on the first example, and we said, okay, well, we have a neuron that's responsible at just the top part of the image, but I have another neuron that can detect it in the middle, and another neuron that can detect it at the bottom. Well, you know, in some ways, I can use an upper level feature, say this guy here, and say, you know, maybe you want to build a line detector that's invariant of position. Okay, so I'm going to take all of these inputs. If any one of them is on, I'm going to say that's a good line. If all of them are off, then there's no line that's detected. Okay, something like that. Okay, and so what we might find is we get detectors of all different sorts. We have straight lines, we have circles, we have textures and other things that are all being created from the data, because our loss function is saying those things are helping with actually getting better judgments about whatever downstream task we're doing. Okay, so to know that we have some of these features, we might say, okay, we actually have the digit 6 in our image. Okay, and actually we try to do that, and we can actually see this when we look at actual pictures, okay? So we can look back after we've trained an algorithm, either by giving it random pictures and not telling anything about it, just try to find some representation, or when we're asking it to learn a category, you know, for example, learn that there's cats or dogs, okay? So it doesn't matter whether it's supervised or unsupervised, like it says at the top, okay? We can put all of this in our network, and then sometimes we're going to find features that are really interesting, okay? So for example here, what we're seeing on the right-hand side is a particular figure that activates one particular feature, one of the neurons in a layer very strongly, okay? So it means when I'm getting the input, okay, on something like this, okay, this particular guy here, okay, might be taking all of these 64 different inputs, okay. The one that's activating most highly is going to be an image like any of these, okay. Any of these guys would be good. Okay, So for example, this guy here looks like there's a very strong horizontal line somewhere in the middle of the input. Okay. Okay, like I said, we can take those basic primitive features and look at how those are engineered for higher and higher layers. So here we have layers 5. Let me see. Okay, layer 5 here, layer 4, and layer 3 in a neural network that's stacked. So 5 is closer to the output. And you can see what's happening is that the layer 3 outputs, they are sort of like more primitive, right? You've got basically lots of patches of color, some that are sort of like textures, etc. These are actual images that activated very well for those layers, okay? Or something like a natural texture here. And then layer 4 is again starting to specialize. You can see there's a bunch of dog faces here. There are some pictures of straight lines, some mechanical objects, and things that have swirls, right? And these get more complicated as we go farther up and closer to the output of the network, okay? So here you can see faces, for example, and other types of complicated machine objects, okay? So basically, when we went back again to our linear lecture and say, well, linear algorithms are very simple. Can we do something more complex with them? We said we're going to have a nonlinear mapping, right? So now the nonlinear mapping is being learned by the neural network in previous layers. All of these primitives, okay, at layer 3, all the ones that are over here, okay, of these primitives in layer 3, they're used in some type of linear combination to create things at layer 4, okay, detectors at layer 4. And the layer 4 detectors are, again, similarly linearly combined and put through an activation function to detect things at layer 5, okay? Okay, so that's what we're doing. We have a convolutional neural network that can do all of these things. Okay, we can apply it basically wherever there's some type of spatially local information. Okay, spatially local, right? So here you can see again, we are thinking of about a particular um, feature kernel, okay, being sled, okay, over the entire image. So maybe starting at this point, but going across horizontally and down, looking for something. And every time it's running this convolution, basically this, theta, okay, this formula, this creation of the signal, it's going to output one number here, okay? And it's going to do it for each time we have a square patch that's being applied against the convolution and then outputting a corresponding number on the output, okay? So these are called feature maps, okay? The idea that we are taking the convolved value, that's basically the dot product of all of the weights, okay? And then we have these feature maps, and then we can do other things with them. Like you can see here, we might want to downsample them through a subsampling layer, okay? Meaning that I'm going to take the output of the feature maps and put them into a smaller resolution, okay? And then I can do the same thing again. I can use a convolution, okay, to get another feature map, a set of feature maps, and then again, do some subsampling, and then do it again, okay? So why would we be doing all of these different features? Okay, the 4 feature maps, Akansha, is because there might be 4 kernels, okay? 4 of those 3 by 3 or 5 by 5, whatever, kernels that we've designed, okay? That we are going to let the neural network try to figure out what weights they are and to slide those maps over the entire image, okay? We get, for each kernel that we have, we get 1 output feature map. So to get 4 feature maps means we have basically four different boxes of kernels, right? 1, 2, okay, 3, 4, okay, which would have, let's say, for different groups of numbers, okay? And these would be calculating over these. So one of these might be the output of the red kernel. And then, in a subsequent convolution layer, let's say this one over here, whether it's 4 or 6 or 8 is really an engineering decision, okay? Basically, what we're saying here is that, okay, is that we have a number of primitive features, okay? This is the number of simple features, okay, that describe something well, okay? And then we can say this is a number of more complicated features. Okay, so it depends on how you think about your image, okay, or the input that you have, okay? After we do all of those subsamplings, we have finally a set of feature maps at the end, right over here, okay? And we're going to put them through a fully connected layer, okay? Exactly like this one here, that's going to determine our output, okay? So as you can see, what's happening is I'm feeding in the first 3 inputs, then I'm going to slide this image, okay, this kernel down to another part. I'm going to get another set of inputs, okay, and then slide it down some more, and then get another set of inputs. So it's basically just moving this box around, okay, and each time putting another point, okay, until I get to the bottom right-hand corner. Okay, so that's the idea. This is one set of weights that's being trained over the entire image, okay, the entire input. Okay, so this is why we call them tide weights. Okay, this one set of neurons that we are training to get whatever values we have set for them, just like the ones you saw in the image box just now. Okay, we're trying to learn something like this, right? Learn these weights, okay? We are learning them by virtue of sliding this window, this 3x3 window, or however big it is, across a whole bunch of images, okay? And then seeing how the loss is going to change with respect to how we're setting these weights, okay? So pooling also tries to downsample resolution and help generalize, okay? So typically when we do that, we're looking for trying to find similar features over different layers, okay? So here we can see this idea of a max pool, okay? So a max pool says, if I look at an activation map, okay, like the ones that we saw on the last slide. So here's an activation map here. Okay, and what I'm going to do is a pooling layer. So this is a max pool layer. That's what it says, MP1, which is basically going to take a 2x2 spot, okay, and make it 1x1. Okay, so for example, here, okay, here I have a 2x2 grid of scalars. I'm just going to take the maximum of these and then put it in a 1x1 square as output. So you can see that this guy, and this guy got stuck here, here, and here, right? Okay, so a max pool just means take the maximum of all the integers or scalars that are in this region and then forward it out. Okay, so why would I do that? Okay, the idea behind a pooling layer or a max pool layer is basically the idea that we want to find a feature and forward it to the output. Okay, so for example, if in this this space here, I had a circle detector. The circle detector really didn't see one here, but it sort of saw circles here. So does this block have a circle or not? We would say yes, okay? So we just take the maximum and put it out, okay? And here, there's no circle, but there's circle here and here. So I'm gonna say, yes, there's a circle here. And for all of these down here, it doesn't really look like they have very high values. So I'm just gonna, again, say that these aren't particularly high values. Okay, so the idea behind a max pool is if one of the regions in that space actually outputs a high value to say, okay, I found something here, there's something here, okay, then at the upper level, you also want to propagate this information out, okay? This makes sense, and a lot of times when you have a face that's very close to the camera or a face that's very far away, right? They're in different resolutions, but we'd still say there's a face, right? So we want to be able to give this scale and variance information in, and we do that by pooling. Okay, so how do we train a deep neural network? So we've gone through two different types. We went through the RNN and the CNN very briefly. Okay, both of these have the same idea, which you're going to basically try not to build fully connected networks with all of the things connected. We're only going to use some edges in some specific way to either cater for the fact that things change over time, or things could be the same in different regions of the image or input. Okay, that's what the CNN is for. How come I can't write? Okay, there we go. Okay, so the usual way we deal with it is backpropagation. Okay, but what happens is we actually have this problem that we alluded to called vanishing or exploding gradients. Okay, and this is because when we propagate the loss from the back towards the front of the network, okay, from the layer L all the way to layer 1, the amount of the gradient gets smaller and smaller. Okay, let's see this for a second. All right. So to describe that, let's look at this slide here. Okay. I'm going to try to move it so that it's easier to see. Okay. So here we have a sigmoid function. It's a nonlinear activation function. And let's just pretend at the beginning, okay, in our penultimate layer over here, okay, we get a gradient and it's not bad, okay, it's somewhere around here, okay. And then we are trying to propagate this back one layer, okay, to the layer over here, okay. And what happens is they get a gradient to learn on, which is this number, but when they calculate their gradient, oops, okay, when we calculate their gradient going back a little bit more, okay, let's say now the yellow layer, that gradient is going to get even more positive if it was already positive, or even more negative if it was going to get negative. You can see what's happening is that the gradient is going to get either a larger and larger s, or a signal, or a smaller and smaller s, okay? And either way, what happens is we're getting to the part of the sigmoid function that is fairly flat, okay? Flat meaning not having a lot of gradient, okay? So the more, the farther back I go in the gradient, okay, the flatter this function gets, and the less I can change my weights over time, okay? I need gradients sort of in this middle zone where there's a noticeable slope, okay, for me to change the weights in a perceptible manner, right? If I get a gradient that's almost flat, like out here, or almost flat over here, basically I'm not going to be moving my weights much at all, okay? And that means as the farther back in the network I go, the slower and slower it trains, okay? And that is a problem, okay? What happens at the end of the day is you see this problem is that earlier layers take magnitudes more time to train than layers close to the output. So these train fast, okay? These train slow, okay? That's an artifact of having an activation function like this. Okay, so what we want to do is change to use a rectified linear unit, right? So the idea is to get rid of this problem where we have these flat segments, okay? And and use the full gradient that comes back from the loss function, okay? So here we can do that by just having this very simple function, okay? And what this function basically does is say, you know, if I get a negative signal, okay, turn off the neuron, okay, don't let it output, okay. You can think of this sort of like a biological equivalent. If you've studied a little bit of biology, you know that when neurons receive input from other neurons, unless they get enough input, they don't do anything, they just sit there and do nothing, okay. So the same is here, okay, you get input, but if the input doesn't cross the positive boundary, I don't do anything with it, I just say Sorry, I'm not involved, okay? So I give 0 as the output. I don't update anything because my gradient is 0, okay? On the other hand, on this side, I let the full gradient pass in, okay? If I get a very positive signal, I'm going to send out the same slope all the way backwards, okay? A slope of 1, right? But if I get a slightly positive signal, then I'm just going to send that back, okay? So that's why it solves these two problems, okay? One is that it doesn't have the saturation problem where the gradient is flat. It doesn't have this. It's always a full gradient of 1 in the positive domain. It doesn't have any complicated function, right? It's just a simple max operator, okay? And it doesn't have any second or higher terms in terms of the cost functions, okay? Okay, it is very importantly a nonlinear function, right? Because now I have a 0 part and a full x part, right? If I just did something like that, well, that's a linear function. Then I wouldn't get any difference than if I stack a network together. Okay, so another problem that we saw was that when we were trying to train a network, okay, a deep neural network, we have to initialize it very carefully, okay? If we don't get a network that's initialized well, we are going to have fall into a lot of local minimum, okay? Because there's so many parameters now that we need to make sure that we initialize quite well, okay? So what we can do is use unsupervised learning to set the network first, okay, before we try to do actual learning, okay? So that's why we say when we're actually supervising a neural network, if we're not training it from scratch, we do some pre-training, okay? So we talked about this at the beginning of this help session when I think Leslie asked some of the questions here, okay? So we talked about this a little bit, that this idea of good representations for one task that just help to generalize what the data is. Okay, so this is unsupervised because it's not conditional on anything, right? So if I can characterize an image or an input sequence without respect to a downstream task, maybe those types of representations are good for doing something with it, right? So if I know what images generally look like, I know what colors they are, I know whether they have sharp corners or not, okay, maybe that information is going to help me describe what types of images are in one class and what types of images are in another class, okay? So one way to do that is by taking the input, okay, and trying to recreate the input. Sounds like a really terrible idea, okay, but it actually works very well. Okay, this is the idea of an autoencoder. It sounds exactly what it sounds like, meaning it's a network that tries to give back the same thing that you gave as input, okay? And the way we do this is by compression, okay? So later on, when we get to unsupervised learning, we'll talk about dimensionality reduction. But basically, what we have is an input layer, okay? And we want to create back the input layer on the output. But we only get a small number of intermediate nodes, okay? So those nodes have no choice. They have to compress all of the useful information about the input into a smaller space and then use that to recreate the input, okay? So you can imagine what would happen if I gave the same number, okay, let's say it's 6 here, okay, the same number of nodes on my input as output, but my middle layer also has 6, okay? Would it help? Well, no, it's first not sparse, okay? But the second problem is because then I would have enough nodes that I can just connect one to each other, right? Can do something like this. And then I would correctly just regenerate it, right? No problem, okay? But I'm not actually trying to make the problem hard enough for the network to generalize, okay? So that's the idea, okay? What we want to do is encourage the small number of neurons in the middle, okay, to recreate what came before it, okay? So for example, in the beginning part of this lecture, okay, let's come back here, right? When we said this would be our input features, okay? Maybe 256 pixels, okay? And in the middle, what we would do is say, train layer 1 here, but not have 256 neurons, maybe just 64 or something like that. So we have a very, very big reduction in the space that's used to represent the entire image, okay? And then I would use this process that we just talked about, okay? Sorry, I think it's 34. Yeah, okay. Jumped one too little, okay? To be able to recreate the output, okay? So if I can do this and I can say, well, this image that you've got here is actually consists of 7 corners, 5 straight lines, a patch of gray and a patch of green, then I can semantically try to encode that in a smaller amount of representations, right? These sort of primitive representations, okay? So that's what we're doing here. We're using an auto-encoded representation, training against something like trying to represent the original input. Okay, this is what we have as the original input. These two should be roughly equal to each other, okay, in order for my JTrain to be low, okay? But I also want it to have sparsity, right? So this is the part here. This is our regularization error, okay, our augmented error, okay, which says, I don't want you to use all possible parameters. I want you to favor representations that use fewer edges, okay? The fewer edges you use, the less I'm going to penalize you to, right? So if you can describe it in less, you can describe this picture in less words or less features, great. Then I think that's a better representation, okay? Okay, so we do that to train the first hidden layer, okay? Then we destroy that layer, okay? And then we train the next layer on top of it, okay? So at this point, we've actually finished training this first layer, okay? Because we did auto-encoding, now we have a good representation of the image in terms of very primitive features, okay? Then what I'm gonna do is say, can you regenerate these image features, okay? These same features that I just trained on in layer 2, okay? Even using a smaller number of neurons, okay? Okay, and then I can erase that, and then I can do another one, okay? So I can pre-train the images, this network this way, okay? Notice I didn't give any answers. I just showed it images, okay? I just showed it natural language, okay? This is just all unsupervised, okay? And all that I'm asking to do is to take an intermediate representation of neurons here and just try to compress how it's representing that input as initial weights for my network, okay? Once I have all of these things as trained through unsupervised training, then I can do the final part. This final part is the supervision, okay? The supervision is here, right? Because I want to be able to say, take a softmax, okay? And then decide whether that input, this X, was belonging to the class of Y0, which might be airplanes, or Y1, which might be trains, and Y2, which might be automobiles, okay? So that's the whole idea. All right, so we set this part of the network, okay, through unsupervised learning, okay, just as an initialization point, okay, because again, because I have so many parameters, different initialization outputs, different initialization weights might result in very different performance values. I just want to get it to a spot where I have a good vocabulary, can I say? A good vocabulary of features that can help represent the original inputs that I have on the left. Okay, so I have this pre-trained network, okay? Then I do normal supervision. Basically, instead of randomly initializing the network, I have done all of this work just to set the initial values of all of the weights, okay? Then I run the normal training, which is forward propagation, get an error, okay, forward propagation, okay, forward prop, where was my cursor? Forward prop, get some loss function, and then back prop, okay, forward prop, get some loss, back prop, okay? So I do this many iterations, okay, many epochs until I get a network that has optimized its weights, okay? And this is called, as it says here, fine tuning, okay? that after we have done the training, pre-training, we just fine tune. Okay. Now, another very interesting technique that we need to make sure we understand is the idea of dropout. Okay. So because we have so many neurons, they can start to over specialize. Okay. So we want to try to make the neurons generalize a bit more. So what we're going to do is we're going to try to get the network to be more robust. Okay. Not trust any one part of the network to encode important information. So maybe this idea of a circle detector could be placed in several different parts of the network so it doesn't overfit. Okay, so this is what I'm going to do. I'm going to say every time I'm training, I'm going to turn off 50% of the neurons. Okay, I'm just going to go through each of these guys here and then randomly decide to turn them on or off. So maybe like this guy, I say, sorry, you're off for this round. Okay, this guy here, you're also off for this round. Okay, and then similarly for the rest of these guys, right? So this one might be off. And then I end up with a structure a little bit like on the right. Okay, once I had a fully connected network on the left, but now it's transformed to a partially connected network on the right. Okay, when I train this way, then the representation won't be localized to a particular neuron. Okay, so when I train, I do this idea to be able to train with only a subset of my capacity of units. But when I test, I use everything, sort of like in cross-validation. Okay, so this idea is to say, maybe I don't trust all of the features all the time, but just use some of them some of the time. Okay, and when you come back this week, if you're watching the pre-recorded lectures this week, you'll learn about this idea of feature projection, which is in random forest. Okay, which is in the next week's lecture. And this is the exact same idea, just applied in a different context. Okay, this is called dropout. It's applied in deep learning. And then in random forest, it's called feature projection. Okay, the idea that you use a subset of the input to try to get a classifier. Okay, and then because you're doing this many times, because each time you do your training, each time you do a pass of training in neural networks, you have many passes, right? You use a different set of neurons, okay, to train each time, okay? In random forest, we don't use many iterations, but we have many trees, okay? So each tree has a separate set of input features that it looks at, okay? So in summary, these are the three core algorithmic things that made deep learning possible. We already talked about how there were other two things, right? One was the presence of very large data, okay? Without large data, we wouldn't be able to learn. I mean, some of you have this problem in your projects that you don't have enough data, okay? So then deep learning becomes pretty hard to execute, okay? It needs enough data. The second thing that we said was we needed the computational efficiency to do that. That came with GPUs, and playing games was actually a very good idea, okay, because we got this hardware out of it. And the third thing is what we learned today. It's the idea of dealing with training multiple stack layers, okay, through dealing with vanishing gradients, being able to initialize our neural networks well through the idea of pre-training, okay, just basically saying if I can represent the input in some basic way, okay, then maybe it can help me categorize what these inputs are for doing a task. And the third one was that we saw was on dropout, okay? Dropout basically said, I don't want to trust any one particular set of features or nodes. I want to make the network more robust by allowing different parts to deal with it. Okay, so that's the pre-lecture. Okay, so I'm going to stop here for a second and then check our how. So it is 6 o'clock already. So it's actually end of lecture, but we only went through the first half of it because we went through pre. If you want to stay on, I can explain a bit of what's going on in the second half, okay, about what convolutional networks do and how they operate, and same for RNN. So if you have any questions, again, feel free to stop me, put it on chat or somewhere, okay, where I can try to address your queries, okay? If you need to go for whatever reason, I completely understand. You're welcome to go. And then we'll see you for tutorial if you didn't have tutorial today, or next week for the next help session, okay? So with that, I will go in now to the second part of our post lecture. Okay, I'm only going to spend about 10 to 15 minutes on this, unfortunately. Okay. Okay, and as I said before, your lecturer, your TAs, all of us are really here to help you learn. If you feel lost for any reason, write me an email, write your TAs an email. We will make time out for you, and we will commit time to tutor you if we can manage it. Of course, we have a lot of other work to do, but we really want you to have a successful course. Okay, so I know we're not very able to keep up with everything, but we want to know, let you know that we won't try to leave anyone behind. We will try to commit as much time as we can to helping you learn, okay, or connect you to appropriate resources. Okay. All right, so we're going to go a little bit about how the CNN works, okay, so that you have a better understanding about what's going on here, okay? Like we've already said before, basically the idea of a CNN is we take some small group of neurons, which we're going to call a feature map, sorry, not a feature map, okay? We're going to call it an image kernel, okay? And we're going to take this kernel, and there might be multiple of them, like here, there's 4, okay? And we're going to slide them all over the image and then train this neural network, this little part, so that it can understand where in the image something that it cares about activates, okay? So as it says here, the input layer is not fully connected, but just connected for a particular input patch, okay? For example, this particular patch outputs 1 scalar here, okay? So you can see it goes through all of those procedures. Now, this is how we can also represent it, okay? So we have one of these kernels, okay? Let's say this is a 3x3 image kernel or a 5x5 one, okay? This 5x5 image kernel basically has 5 times 5 weights, okay? But because an image usually has multiple channels, okay? Let's say R, G, and B, we might have 3 channels. We actually have 5 times 5 times 3, or so 75 weights in total for this image kernel, okay? We also have 1 bias, right? Because we always have this top bias here that goes in, okay? So we have in total 76 weights, okay? That we're using to represent this golden square, okay? It's actually all of these integers, okay? These are the weights, okay? We slide this image kernel over the entire image, okay? And for each spot that it's at, it outputs a weight, okay? An output, okay? So, you know, for example, when it's over here, it might project a dot here, okay? And so one of these outputs is called an activation map or feature map, okay? And it says here that we might actually have 6 of these guys. We might have 6 different features. Each of these different features is producing one of these outputs, okay? One of these activation maps. So this one here might be producing the first one, for example, okay? And then we would say at this level that the depth of this one is 6, okay? And that the width and height of these would have been changed, right? Because if we did 5x5 convolution, at this edge here, I'm going to get a slightly smaller grid of output. Okay, it will be 28 by 28. Okay, so you can see when we're doing this type of convolution, we're going to actually shrink the image. Okay, the image as a vector shrinks over time because we might, you know, for a 5x5 patch, okay, we're going to get smaller and smaller input. So here, for example, we have a 7x7 input, but we have our kernels are of 3x3 kernels, okay? And because we're doing that, we're only going to get 5 values as output, one for here, one here, one here, one here, and one here, okay? So we only get 5 outputs, okay? If we do other things like skip, okay, do it every 2, then we're going to get even fewer images, smaller resolution out, okay? So stride tells you how long the step size as we go between left and right, okay? And the way to combat that it's shrinking is to do padding. Padding means adding a border of zeros around the original image. So our original image might be here, for example, okay? And then we just add these zeros so that when we convolve the kernel around, we get back something that's 32 by 32. Okay, so after we've done the filter, okay, we've actually created this, again, theta transpose x. We've taken all of those activations. We still have to put it through our nonlinear function, which we call g. That's our activation function, right? So we take the signal, which is our dot product, okay, put it through a nonlinear activation, and we have all of these choices as we saw before, okay? Some of them we haven't talked about yet, never mind, we'll talk about them in a minute, okay? So again, we already talked about the problems with things on the left-hand side, right? That something like the logistic function or the hyperbolic tangent tends to flatline, okay? And then we have problems here, okay? What we want is to something that will pass on the full gradient. So as one of you asked about, if we zero out the ReLU, okay, and we have a 0, units can die off, right? Okay, so maybe we don't want to zero it out. Maybe we want a signal, but a very small one, okay? Not something like a line, which would be just S, okay? But something where we multiply S by some small amount, okay? So then the leaky ReLU would be a function like the blue line there, okay? So we allow the negative information to propagate, but set it at a much lower salience because we believe that, for example, positive values of features indicate something important is going on, okay? We can also parameterize this and use an alpha value, or we can use several pieces of line segments like this one over here, the max out network, to try to learn some way of learning a function, okay? So maybe very positive, but also very negative values are important, but ones that are slightly negative are not so important, okay? Like we said with the pooling layer, okay, remember what that was. We took a pooling layer, which took several integers, just took the maximum of them in a spatially confined region and propagated that up, right? So the pooling layer here is basically downsampling, okay, the input, so to yield a lower resolution image, right? You shrink the image, then the same image detector, the same circle detector can be used to find the same feature but at a higher resolution, right? So if I have a circle detector that looks at you know, something over 2 pixels, then over here it looks at 2 pixels and then looks at 2 pixels over here. This final circle detector, okay, the one over here, okay, is actually looking at this entire picture pretty much, okay, because it's after all the smoothing, okay? So you can see what's happening is when we downsample and we pull things together, when our feature detectors look, it's looking at a much wider resolution of the original input image. Okay, we also talked about the softmax and hierarchical. So softmax activation functions. These are a generalization of the logistic function, okay, to have multiple classes of output. So this is the case that we told you about in the neural network lecture, where we want to detect maybe irises in 3 different classes. So we have something like a logistic curve, but now over 3 different classes or k different classes, okay? And another way we can do this is use hierarchical softmax. Hierarchical softmax is the case where when k, you know, this k gets very large, okay? maybe it becomes very hard to manage because there'll be a lot of underflow, okay, because the exponents that are being calculated here are too small, okay? So when we have, let's say, thousands of classes, maybe we want to use something like this, okay? Convert the flat n-way decision to a set of binary attribute nodes, okay? Where I only have to decide whether the node on the left or the right is a winner, and then I propagate that information at the top. So maybe at the top, it decides that, okay, this particular node is the winner after 4 contests, so to speak, okay? Okay. When we did deep learning, we found out that as a community, things got a lot better as we deepened the network. So in the traditional computer vision in up to 2011 or so, okay, this is 2011, uh, we found that traditional machine learning techniques like SVMs and KNN work pretty well, okay? And you can see these bars indicate error rate, so the lower they are, the better they are. And there was a dramatic improvement, about a 40% reduction in error when people started to think about using deep neural networks, because again, the architecture and the hardware and the algorithms had gotten to the point where they could be used, okay? And in subsequent years, this got even better. So at the point in 2016 or so, we saw that neural networks, when appropriately trained and layered up, could achieve a human performance. In fact, it could perform better than human performance because, of course, machines don't get tired, they don't get fatigued. So they're very good at doing image detection, even better than humans at this point. Okay. So when we design a neural network, let's say a convolutional neural network for vision, typically we see this type of construction. We do some convolutions, okay, to build up primitive features, and then we do pooling so that we reduce the resolution of the image, okay, so that we can apply the same process again. So we're building primitive features here, okay, and then building more complex features here. We're building fine-grained features here, and we're building coarse-grained features here, okay, because these are coarse-grained because the images have shrunk a lot, okay, they're much smaller than the ones on this side, and they're more complex because they build on the features that come from the primitive side. Okay, so that's exactly what happened with the competitor in 2012. It's called AlexNet. That was the breakthrough in computer vision. You take our CV class, Angela will teach you the same thing in much more detail. Okay, so basically that is what happened in AlexNet, is the idea that you use convolutional layers followed by pooling layers, convolutional layers followed by pooling layers, okay? And then finally, the output is going from input here, this is the input, okay, all the way to the output, okay, is to build up all of these things to finally get the class scores. The class scores would be some type of softmax. Okay, so let's see. Okay. Yeah, I'm going to, let's see what I can jump around a little bit more. I'm not going to cover that. We covered transfer learning a little bit already. Okay, so maybe that is an area I want to spend a little bit more time on. See whether I can get this cleaned up. Okay, yeah. So the idea behind transfer learning is something that a lot of people are looking at right now, which is to take a good representation from one problem and use it for another. Like we said before, you can use a pre-trained network that comes from supervised or unsupervised learning, okay? And then basically use it as the initialization values for another network, okay? That network obviously has to have the same network architecture. You can't change what the layers in the middle look like, okay? But then you can add a different layer at the top, a new set of layers at the top, like you can discard the ones over here, okay? And then retrain it for another set of problems, right? So that's what we saw in the lecture earlier when we were talking about transfer learning. Okay, so you can decide when is a good time to transfer. Okay, when the two tasks have very similar inputs. So in computer vision, they're usually, raster images. Okay, that's captured by a camera. Okay, when the task B has less data than a pre-training task. Okay, and when you think the tasks are similar in the simple representation or features that are created for one task is helpful for another one. Okay. Okay, so we can do the same type of thing that we've seen also for natural language, right? So we can actually use transfer learning to create what we call word embeddings for natural language, okay? So we can say that words that are similar in meaning share similar context. So we could say a doctor, a pediatrician, these words like nurses and hospitals would occur in the same type of documents. So words share similar contexts, okay? So that's what this blue part says, okay? Even multilingual words should be near each other. So if you use words, or in Singapore, we code switch a lot. So we change between Tamil and English or Chinese Mandarin and English all the times. So even the same type of word like doctor in one language and another language would see similar contexts. Okay, so it helps to say words in multiple languages also share a similar context. Okay, and you can even generalize this to the multimodal idea. So when you look at images and captions, we can actually show correlations between a picture of a car and the word car, because the representations of cars as a picture and the representation of a word as a set of letters also happens to share similar context. You see an image of a car and it's captioned with the word car, and this is happening more than by chance, then we might be able to learn a representation of car, a visual representation of car can be connoted by a word car. Okay, the final thing that I do want to cover a little bit is on RNN computation. Okay, we said an RNN keeps state, right? And we saw that it basically does this computation where we receive a new X as input, and we get the H from the previous time step, right? These are the purple edges that we're trying to get. Okay, so when we have a state, we basically are computing 3 sets of weights. We need the weights coming from the previous time step. That's our Markov information, right? Catering what was the previous state of the network. We need to cater for the edges that are coming in from the input. And we need to be able to describe how the current state manifests an output, right? So that's the edges up here. Okay, so you can see how this is worked out in a particular RNN. Let's say we're trying to predict characters, okay? And we have a training example that says hello, okay? So we start with an H, okay? So this might be a one-hot encoding where the first dimension is an H, the second one is an E, the third one is an L, and the fourth one is an O, okay? So you can see how we're going to do this. First, we're going to pass it through our hidden layer, okay? And we're going to compute the hidden state going forward. So at this red box here, I need the inputs from this state as well as the inputs from the previous hidden layers activation. Okay, I'm going to put that through a nonlinearity, okay? By going through the softmax at the top, that's our G function, okay? And use this to manufacture all of the probabilities for each of the letters. Okay, so perhaps, for example, this one here, the 0.13 is the highest one, so I have an E as the output. Okay, and I'm going to propagate that information onwards. Okay, so I'm going to use it at the next time step. When I unroll this computation, I do this forward pass here. Okay, I get the E, I use the E as the next input, and then continue onwards. Okay, so I can unroll, what they call unroll, forward propagate this RNN through all the time steps until I finish outputting what I want. Okay, when I output everything, I also have to be able to backpropagate. So what happens if there's an error, right? So you can see what happens is I might have errors at certain time steps. Maybe the second letter that I output was wrong. Maybe I put an I instead of an E. It should have been an E, okay? And the third letter might have been an R instead of an L, okay? And the fourth letter might be right. The fifth letter might be an A instead of an O, so there's an error. So all of these are being accumulated. And at the very end of the sentence or whatever I'm doing to compute this sequence, I have a loss function, right? The training loss, okay? Now, after I've done that, I also have to backpropagate. I have to take that information and try to change all the weights on my network, okay? And so I have to go all the way back to the first time step, all the way back here, okay? So that's very cumbersome. And so people decided that it would be a good idea not to do all of those calculations, because as we know from reinforcement learning and other lectures, that the last state, the last piece of history is the most important. So what we do instead is we do backpropagation truncated, okay? We say instead of doing it all the way through the network, we're just going to say partition the network up and then stop at some point. So we're going to propagate it. And then after this point, we're going to say, that's it. This is the loss for this part of the network. For this part of the network, I'm just going to take the sum of these two losses. For this part of the network, I'll just take the sum of these three losses, okay? And I'm just going to backpropagate and think of them as basically problem 1, problem number 2, and problem number 3, okay? Even though this is one sequence, I'm just going to compartmentalize it so it's not so difficult. Okay, and that is actually the end of the lecture. I'm sorry, I'm going to have to run because it's already 6:20. I hope you were able to get something out of the help session. If you have any additional questions, again, please ask me through email or other ways. We'll try our best to help you. Okay, so I appreciate it that you attend, and I see many of you regularly, so I'm very glad to see you every week. Okay, so again, if you have friends that are suffering any difficulties, ask them to come so we can get their questions answered as well. Okay, thank you everyone. Have a good day.